Let's consider addition reactions of alkenes. And the first of those addition reactions which alkenes get to undergo is electrophilic addition of substances which are in this form HX. So it's necessarily not hydrogen only, but it can be anything that is attached to another one. So when you get to attach or get to react these substances with alkenes, what gets to happen? So the rule that gets to apply is the Markov-Nikov's rule. So when you have got a substance, let's say we have got this substance like this, and you are getting to react this substance with, let's say, hydrogen bromide. So this rule says on the part, on the double bond, on the part where you've got a double bond, you have got, of course, two carbons. You have got a carbon that has got a lot of alkyl groups and a carbon that has got a lot of hydrogen. So this Markov-Nikov's rule tells us that the hydrogen or the electropositive part is going to attach to the carbon that has got a lot of hydrogens, and then the halogen or the electronegative part gets to attach to the carbon that has got a lot of alkyl groups. Now, as a reaction mechanism, since this carbon has got two hydrogens, this one has got only one hydrogen, meaning that it is this carbon that gets to attack this hydrogen. And when that happens, this bond gets to break. So what you are going to have as a product is, because the hydrogen has attached on that carbon, the double bond that we are seeing is going to be broken. So what you are going to see is something like this. Now, this carbon which is here is going to lack hydrogens, or it is going to lack atoms, because this hydrogen has attached to this one. So this carbon here has now three hydrogens, and we know it is stable, but this one has got only three bonds, so it is going to remain with a positive charge. So this carbon here, because it's bonded to three other carbons, a tertiary carbon, and it is a stable cation. Tertiary carbocations are very stable, right? And then you have got the bromine, which has gained two electrons, and so it is going to carry negative charge. So as a reaction mechanism, now what happens is this bromine now attaches to the carbocation. So now what we are going to see at the end is this compound being formed. So in this reaction, this is the major product that is formed. It is because it is formed from the tertiary carbocation. The same reaction, we can also show another product that can be formed. So now what happens if the hydrogen attaches to the carbon that has got a lot of alkyl groups instead of the one with a lot of hydrogens that attaches to this carbon? So again, the double bond is going to be broken. So what we are going to have still is this. Okay, something like that. Now, this carbon which is here, because the double bond is going to be broken, it is going to lack one proton, because the hydrogen is attached to this carbon which is here. So because of that, it's going to carry a positive charge. And then we have got this bond also breaking between the carbon and the bromine. I mean the hydrogen and the bromine. So we now have bromine minus. Now the bromine can now attach to this carbon, and that is now going to give us compound something like this. So this one is going to be a minor product because it is formed from a primary carbocation, and the primary carbocation is not stable, and so even the resulting compound is not stable. So the major product in this reaction is this one. We can consider the same compound that we have used. Now let's say we are reacting it with this compound. What is going to happen now? First, we need to determine which one of these two is the most stable. I mean, is the most electronegative. So chlorine is more electronegative, meaning that these two electrons are going to be pulled in this bond to the chlorine. So in this case, the iodine is the one which is going to be partially positive. Now, according to Markov-Nikov's rule, is that the carbon which contains a lot of hydrogens get to attack the more electronegative atom, and the bond gets to break like that. So the result, so because we have attached the iodine to the end, we are going to see the iodine at this point like that. So since we have attached it to the end, this carbon is going to remain with a positive charge because it has got fewer than normal number of bonds. Then we have got the chlorine minus. Now the chlorine can come and attach to the carbocation. That is going to give us, this will be the final product in this kind of reaction. So these are electrophilic addition of substances that are in the form H of X. So this is the first kind of addition reaction that alkenes get to undergo. Another kind of addition reaction which alkenes are able to undergo is acid catalyzed hydration. So hydration meaning we are getting to add water. Now we know that when we have got alcohol, we get to break it using an acid. We are going to form an alkene. So what happens when you have got an alkene? You get to add water in the presence of an acid. So the reverse reaction happens because the dehydration of alcohols gets to give us alkenes, meaning that the hydration of alkenes is going to give us alcohol. It's just a reverse process. So say we have got this compound and we get to react this with water. So basically when we are talking about water is, water undergoes autoionization, and in that process what we are going to have is the H3O plus ions. So these ions are the ones which are going to provide us with those hydrogen ions which are going to be able to attack this compound that we are able to see at this point. So now because we know that, I'm going to put just the HO3 plus. You know that this oxygen is going to have two lone pairs of electrons and then it carries a positive charge. So what is going to happen? The acidic proton is going to be attacked by the carbon that has got a lot of hydrogens on the double bond. So when that is grabbed, the result which we are going to see is that we are going to have something like that, and then a hydrogen is attached at that end. Because the double bond has been broken by the addition of the hydrogen, this one which is here is going to remain as a carbocation. And we have got water also as a product because we've grabbed one hydrogen. So this is also a product. So this is a slow step and it is a rate determining step. Now when we have got this, remember we still have water in this reaction which was produced. So the water which we have will again get to react. It's going to attack now the carbocation. And this water molecule is going to attach at that end. So what we are going to see, we're going to have something like this. Now I'm not going to show the hydrogen on top because basically we don't show hydrogens when you're dealing with organic chemistry. So we're going to have something like this, and then at this point we have got the O which is bonded to two hydrogens. Remember it had two lone pairs, which is 4 electrons, so it has remained with one lone pair because one is the one involved in the bond which has been formed. So because of that, this oxygen is going to have a charge of +1. Why? Because oxygen has got 1, 2, 3, 4, 5 electrons in the outer molecule, but we know that oxygen is in group 6. So 6 minus 5, that gives us a formal charge of +1. And then from here, what is going to happen is that another water molecule is going to come and react. So again, the oxygen has got lone pairs of electrons. So this is going to grab one of these hydrogens. What we are going to have is the oxygen with only one hydrogen like that, and then we are going to have H3O plus, because one hydrogen is still attached to the water molecule, and so you have got three hydrogens on that compound. So this is the mechanism that gets to happen, and this reaction also gets to obey Markov-Nikov's rule, and it is a very useful method of getting to prepare alcohols. And so we can see we started with an acid. At the end, an acid is still regenerated, but we've transformed the substance from being an alkene to being an alcohol, and this is an equivalent alcohol. This one had four carbons. Even this alcohol has got four carbons, so it is the equivalent. So same, when we get this alcohol, we get to perform an acid catalyzed dehydration. We are going to get this substance which is here. If it is hydration, same in the opposite direction like that. So say we have got also this compound. What would be the name of this compound? You can see this is portion number 1, this is number 2, this is number 3, this is 4. Portion number 3 we've got 2 methyl, so this is 3,3 dimethyl but 1N, or butene, 1 butene. So in the presence of an acid, so we don't only use water as the acid, we can also use different acids, for example sulfuric acid and all these different acids. So we are going to use sulfuric acid. Now we know that this is in aqueous solution, so water is still present. So from the auto ionization, we are still going to have the H3O plus. So we are going to still have the H3O plus here with a positive charge. And again, the double bond, the carbon that has got a lot of hydrogen on the double bond is going to grab one of these hydrogens. What we are going to see, the double bond breaks. This carbon which is here is going to remain with a partial positive charge. Now, when you are talking about these carbocations which are formed in this kind of reactions, whether elimination or addition reactions, there is some rearrangement that gets to happen in these reactions. Okay, there's going to be a rearrangement. If we get to look at this carbocation, this is a secondary carbocation. Now, what happens is that one of these methyls can shift from this position and attach to this position. So what are we going to be able to see now when that happens? Because we have seen the shift of a methyl, we have just remained with one. One methyl is going to come and attach at this point. Okay, so we're going to have something like this. So the charge moves from where it was to where the methyl has come from. So what is this carbocation? So we can see we have got one group here, two groups, the third group there. So this is a tertiary carbocation. And the reason as to why these rearrangements gets to happen is because a tertiary carbocation is much stable than a secondary carbocation. So that is why the rearrangement has gotten to happen. We know that in this reaction, water was also released because we only grabbed one hydrogen from there. And this is the rate determining step. And then the product which we have at this point, that carbocation which we have, I can as well write it like this, with a charge at this point. This one still gets to react with the water which was produced. So this goes to attack, the oxygen attacks the carbocation at that point. So what we are going to have, we are going to have something like this with the oxygen which has attached, which has got two hydrogens like that. So this oxygen is going to have also a partial it's going to have a positive charge. Why? Because it has got more than enough bonds. Again, another water molecule is going to come in and be able to grab that oxygen that we are one of these hydrogen that we're able to see at this point. So one water molecule is going to come in. So the oxygen comes and grabs that hydrogen. So what you are going to see is now just OH. Then you are going to have this. Okay, this is not supposed to be there. So this will be the product, and also H3O plus as a product. So this is the final product in this kind of reaction, and this is the major product that is being produced after the rearrangement got to happen. Now say if the rearrangement didn't happen, what would be the product? So if we just used the the same one which we have at this point, so let me just take it from here. You get to react this with water. So the water would have come and attacked this carbon, and the result would have been that the oxygen would carry a positive charge because it has got a lot of bonds. And then another water molecule gets to react with what we have here. So that water molecule is going to grab one hydrogen at this point. So what would we have? So we are going to have now just the OH as a product, and also H3O plus. So this is a minor product that has been formed from the carbocation that is secondary. The major product is the one formed from the carbocation that is tertiary. So acid catalyzed hydration do not yield primary alcohols to any important extent. So what they will get to yield is either a secondary or a tertiary alcohol. Except when you're talking about ethene, when you get to do the catalyzation of ethene, you might be able to produce a primary alcohol, but generally you don't get to have primary alcohols. Alright, another kind of addition reaction which alkenes are able to undergo is electrophilic addition of high halogens. So what gets to happen when you get to add halogens? So we have got what we call vicinal dihalides. So vicinal dihalides are going to be formed from the reaction of either bromine or chlorine. So these are the two elements that we need to take note of. These are very, very reactive. So this is in non-nucleophilic solvents. So electrophilic halogen addition to the double bond of alkenes follows anti-orientation. So what we mean when we are talking of the vicinal dihalide is we are going to have the same halide. They are going to be differently oriented, meaning that you are going to have on opposite sides. So for example, let's say we have got ethene. You get to react with we get to react this with chlorine. What is going to happen is the chlorine gets to attach on this ethene. The result to be an alkane I mean. So that will be it. And it follows this way because the result is always and orientation. They are always in the opposite directions like that. So we form more like trans products. Okay, let's say if we have got this, we get to also react in the presence of bromine. So what you are going to form is bromine, like that. So it is actually this reaction, the electrophilic addition of halogens, which is the test of unsaturation. So when you talk of bromine itself, so when you are using bromine, this the compound that you started with, which is the ethene, this one is colorless. But the result that you are going to have after you get to add bromine is something like bromine itself is reddish brown, so the result is going to be also colorless because this one is reddish brown. So you've reacted something that is red with something that is colorless, and then you get something that is colorless. Just know that you are talking about alkenes or alkenes, those with at least a double bond. But for alkanes, if you react it with the bromine, the change of the color will not be seen. So this is the test of unsaturation that is used. Okay, let's have another example. Let's say we have got a double bond, but instead of it being a thing, we have got butene. Okay, so here we have the compound, and in the present, you are getting to react this with bromine. What gets to happen then in this reaction? So I can show bromine like this, and you know that each bromine has got three lone pairs of electrons. So actually the first thing that is going to happen this as a mechanism, if you want to show the mechanism that gets to happen for this reaction, is that this double bond, remember we had mentioned to say double bonds also act as nucleophiles. They also love the nucleus because they 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 do not have enough electrons. So this is going to be able to attach to this point. Bromine itself is also a nucleophile, so this one also gets to attach like that to that point. So when that happens, this bond is going to be broken. So what we are going to have, the double bond is broken, but we still have this. Now notice that the bromine is also attached at this point. It has formed two bonds like that. Because it has got more bonds, it's going to carry also a positive charge. Remember, another bromine has been released in the process, and this one carried the two electrons, so it's going to have a negative charge. So again, what is going to happen is this bromine which was released is again going to attack. So it's going to attack one of these carbons. So if it attacks this carbon, this bond is going to be broken. The two electrons will go on this bromine. So it will always be on the opposite directions. And so what we are going to see is we have got this bromine. Let me write this properly, okay? We are going to have one bromine, so we have attacked. This bond has remained at this point, so we have got a bromine here, and then the other bromine has attacked and it is attached on top like that. So this is going to be the product that we are going to be able to see. So it is not the only product. We are also going to have the other enantiomer, meaning that the opposite orientation can happen. Okay, the opposite orientation is able to happen. This can be also down, this one can also be on top like that. So let's get to consider also this one on this kind of reactions. What happens when you get to react this with bromine? So same, one bromine is going to get to attack the double bond. Okay, one bromine gets to attack the double bond. So the first thing that gets to happen as a mechanism is that we have got this bromine attached to another bromine. So this double bond gets to attack this, and then the bromine also gets to attack like that. So this bond is going to be broken. So the double bond is going to be broken at that point. So what we are going to have is something like this, and then this is attached to a bromine like that. Remember, a bromine is also a product in this kind of reaction. That bromine which was produced will come now and break one of these bonds. When it attaches there, meaning that this bond is going to break. So what you are going to see as product is that one bromine is going to be like this, another bromine is going to be like that. So the two are going to be in opposite directions. We have got the anti-orientation. They can't all be like that. That product is not possible for this kind of reactions. So this is what gets to happen in the electrophilic addition of halogens. So let's also consider the last reaction that we can talk about on alkenes, which is the halohydrin formation. Now when you're talking about halohydrin, this is just the hydrin is just representing alcohol, so that is halo alcohol. So the formation of this compound. So what gets to happen? How do you get to form alcohols from alkenes? When you have got an alkene, let's say ethene, to form an alcohol, the first thing you are going to react it with an halogen and then also react it with water. So what you are going to see in this kind of reaction is that the double bond is going to be broken, and this is going to be the product, which is the halohydrin, which is the major product. We're also going to have another product, which is a vicinal dihalide, and you're also going to have this product. So we're going to have three different products, but the major product is the halohydrin, which is this one, the alcohol that has been formed. We can give an example of this, how this mechanism is getting to happen. So say we have got butane. And then we get to react this one with X. Now the X which we are talking about can either be bromine or chlorine, not anything else. So those are the two. So let's say we get to react this with a chlorine. Now we know that chlorine is a molecule, so it always exists like that. So when this happens, what you are going to see is that this this double bond gets to attack the chlorine, and then the chlorine also gets to attack like that, and then this bond is broken, just like we saw on the previous reactions. So again, going to see a chlorine which is going to attach like that. Again, chlorine is also a product in this reaction. Okay, again, this chlorine which has been produced as a product can come and break one of these bonds. When this comes and attaches here, what happens to the bond? The bond is going to be broken. Okay, the bond is going to be broken there. Now instead of the chlorine coming to attach, because if the chlorine is the one which is going to attack, then the reaction that we are going to have is halogen formation. I mean the same as the previous one, which is the addition of halogen. So instead of the chlorine which was released coming to attach, this chlorine is going to be a product. So take note, we already have one product. Now because we also react with water, so we are now going to have water coming in. Water has got two lone pairs of electrons. So this is the one that is going to come and attack. So let's say it attaches at this point, meaning that this bond is going to be broken. So the product will no longer have a double bond. Actually, just from here, we no longer have a double bond because we have got the attachment of the chlorine. Sorry that I wrote the double bond, I didn't notice. So what we're going to now see is that we have got this one down. We have got also this on top and this one. Now the chlorine is going to remain here because the bond has been broken. Okay, and then on this end which is here, we also have this, of course, but we also have the attachment of the O like that. So this is going to carry a positive charge because it has got a lot of bonds. The next thing that gets to happen, another water molecule is going to come in. The oxygen is going to come and grab this one hydrogen. So what you are going to have, you have that, you've got this, you have got a chlorine, also have that, and then you are going to have now just the OH, and then plus H3O plus. So this is the reaction that gets to happen. So we have got this product, we have got the chlorine as a product, and then we have got the halohydrin as a product. We have got an halogen and then an alkyl functional group. So that is now the halohydrin which is formed. So basically this is what gets to happen. So if you are talking about these which are circular, the circular alkenes, and you get to react this, let's say, okay, in the presence of water, you get to react it with bromine. So the two products that we are going to be able to see is the double bond has been broken, so we are going to see OH at this point and then the bromine there, or you can see another product where it is the OH which is in front and then the bromine is in the back. So these we call them racemates or lenzemic mixtures. They are basically the same, but they've just changed each other's orientation. So these are the two possible products that we are able to have from this kind of reaction. Let's consider the last example in here, then we are done with this tutorial. So let's say this is the compound that we have, and we first react with the bromine, and we'll consider where the double bond is. So what happens is that the double bond gets to attack like that, and then the bromine also, the lone pair, gets to attack, so meaning that the double bond is now broken. In this kind of reaction, one bromine is going to be released. So what you're going to have is that now, because we have broken that double bond, the bromine has attached like this. The carbon is going to remain with this carbon here is going to remain with less number of bonds, so it gets to carry a positive charge. Okay, it gets to carry a positive charge. Actually, the one which is even going to carry a positive charge is even the bromine, because it has got a lot of bonds than enough. Now from here, what we are going to see again, the water comes in. The water is going to be able to break one of these bonds, and it attacks from the opposite direction. So if it attaches like that, the bond here is going to be broken. Then what we are going to have is the water which has attached at this point, and then the bromine is going to remain here. Remember, this is water, so that is OH2. Another water molecule is going to come in to grab one oxygen from here. I mean to grab one hydrogen. So what we are going to have as a final product, we are going to have this as a final product, and then H3O plus is also going to be a product. So that is going to be the mechanism for this reaction that gets to happen, and these are going to be the different products. Thank you so much for watching this tutorial. Stay blessed.